Hi, good morning. This is the Gardener community meeting. Today we have a packed agenda, so we have a lot of topics. Maybe we have to move the last one to the next meeting, depending on how the presentations are going. So, Daniel, are you already ready? Can you start? You're still muted.
Do you hear me?
Yes.
Perfect. Okay. Yeah, I could start, sure.
Okay. And I'll stop sharing.
Can you see my screen?
Yes.
Okay, perfect. So, good morning again. Today we are talking about a new feature that was introduced. It's to allowing to opt out of automatic machine image updates. So previously, there was an image update every day when there was a new machine image version available, and in a defined time frame, basically, that was set in the shoot. Now there is a flag introduced in the shoot manifest, an optional one, where you can specify whether you want to update every day or if you want to postpone it until a certain force update time that can be configured in the cloud profile. The specific flag is in the auto update section, so in the spec, maintenance, next to the Kubernetes version that we already know this flag. There's another one that's called machine image version update. And the default for this one is true. So if you don't do anything, the behavior won't change to the previous behavior. There will be an update every day. How does the cloud profile look now? There had to be some changes introduced. On the left-hand side, there is the old version of the cloud profile, mainly specifying machine images with a name and an image version. The names are unique, and that's also how it stayed. It stayed unique in the right-hand side. The right-hand side is the new version that got introduced. The major change here is that there are multiple versions for one machine image now. You can see here CoreOS now has different versions, ranging from a lower to a higher version. Change here is that Semver is enforced now, so it has to be a Semver version, and yeah, that will be made sure when you apply the cloud profile. In case the machine image version doesn't have a Semver version, you can map it in the extension. So you have to tell the extension provider this one Semver version maps to this image. But this is if you want to know how explicitly how to do that we can do that afterwards. So one other change is, of course, we need an expiration date. This is also optional. So in case you have an old version, like here, we have in this example we have two versions for CoreOS. We have the 2023 version and our demo, this beta version here, and this one should be updated. So it has an expiration date set, and after that, every shoot that goes in the maintenance timeframe after that expiration date will be forcefully updated to the 20.3 version. So you can basically be sure as an administrator, all your shoots were updated in time. And the expiration date is of the meta v1 time, the go time. So maybe a quick note regarding backwards compatibility. In the cloud profile, you can still specify machine images the old way. Name and image, this is still accepted. We just converted to the new version, basically, that adds this as a version in the versions field. Yeah, so nothing will change from this side. Let's go on to a quick demo. 1 second. I think I need to share another screen. 1 second. I'll just stop sharing real quick. Now I'll share the screen. Okay, now you should see the other screen, and you should see some terminal windows. Is this correct? Okay, fine. So what we see here is basically on the left-hand side, the cloud profile that is having, I hope it's not too small, but this is having a machine image version of 2023.5. And yes, I will create a shoot now in the background. 1 second, it will pop up here in a couple of seconds. So yeah, here it popped up. We have an integration test shoot here now. And in the background, I'm just executing some integration tests that I don't have to do it manually. But you will see the changes here that I can talk about. In the cloud profile, I just added here a new image version, the 001 beta version that has an expiration date set. And this expiration date is actually yesterday. And I created a shoot. Let's take a quick look at that shoot that got created. The shoot has the machine image version, automatic machine image version update set to false. So it doesn't want to update every day. Rather, it waits until the force update is. And it's also on this 001 beta version. And this version has, as we can see in the cloud profile here, an expiration date set. So we expect that in the next maintenance time window, there will be an update to the shoot to the highest December version, and that is the 2023.5. Now we simulate basically that there is a maintenance time, and we do this real quick by setting an annotation. 1 second, I'll do it in the background. Let's refresh this quick. So we have this operation maintain, in case you didn't know. You can set an annotation and simulate basically that you're in the maintenance time window. Other than that, the maintenance time window, you can find it under spec maintenance here. But yeah, for this purpose, we just simulated it. Now I will start the Gardener control in the background. It should do this update or should do the maintenance work. And then we can see that, or we should see that the image version got updated. We can check the shoot now. It got started in the background. So yes, we can now see it got updated to the highest December version, the 2020.3, and the maintenance was fulfilled. So the annotation for the maintenance was removed. Yes, that's basically what I wanted to show. There are different cases also. So for instance, there's also the case when you have the machine image version set to true, and you will get an update every day. But because we have a packed agenda, I didn't want to show that all today. But just to know that this is also possible. So thank you very much, and I stop sharing.
Are there any questions to Daniel? If not, then Kristian can continue.
Can you hear me? Can you hear me?
Yes.
Okay. So I will going to show you a quick demo how we can create a different machine images in one cluster. But first, a few words before that. What's different now? We have moved. 1 second. Now we have a machine image specified in worker level, worker pool. The old one is still here, but
are you sharing something?
Oops, sorry. One second.
Now we can see, yeah.
Okay, so now we have a machine image specified in the worker level. We can see it here. And what's different? Actually, this machine image will be taken when the machines are created. And the old one, which is in the cloud level here, is used only when worker level machine image is not specified. And for this reason, let's call this default machine image, because it's used only when the old one is not specified. And what we are going to do, so we can see that the default machine image is Ubuntu, but actually we have two machine images in two workers, which are CoreOS. And here we can see this is the shoot cluster. We have two nodes with CoreOS operation system. So what we are going to do, let's delete the one machine image, and what we expect to happen. This machine image will be replaced by the default one, which is Ubuntu. So now we have machine image CoreOS and machine image Ubuntu. And what we expect to happen after reconciliation, we will have a new machine and new node, which will be Ubuntu. And yeah, it's created, and we are now waiting it to join the cluster. A new node will be joined the shoot cluster, which will be with Ubuntu operation system. And it will take around 1 minute, maybe. If you have any questions, you can ask until it's done. So this is, as I said, this is the default machine image. It's still there, but it's used only when this one is not specified. And how we can create new, how we can create a new worker with new node. Let's copy, for example, this. And let's paste it here. It will be CoreOS again, and just change the worker name, worker 3, for example. We are going to save that, and now after the reconciliation, we will have new machine with CoreOS. We can see here that Ubuntu joined the cluster. Almost, it's not ready yet, but it will be soon. And that's the behavior of this change. If you have any question, you can ask. The Ubuntu joined the cluster. Do you have any questions?
Thank you, Kristian. Seems not to be the case. Then we can go to the next topic. That's Rafael.
Okay. You hear me? Yeah.
Yes.
So I will shortly explain what we have changed with extensibility to allow extensions to mutate any resource that is deployed by Gardener in the shoots. So far we have implemented only some webhooks for the control plane. So for example, the cloud provider config is injected into the kube controller manager deployment and so on. But all of these resources are in the same cluster in the seed. But some providers might also need to modify resources that are deployed to the shoot. So for example, OpenStack the OpenStack provider will soon need to add a special annotation to load balancer services if the newly introduced load balancer class is used, and so on. So the general need exists. Yeah. Let's continue. So just a quick diagram how it looks like. So in the seed we have a namespace of the shoot where the Cube API server is running, and also the other components, of course, that I didn't depict now. And as soon as we have this situation, we can basically talk to this API server and reach our shoot cluster. And into the Cube system namespace of the shoot cluster, we need to install some system components usually. So something like Cube proxy, Calico, the VPN, and so on. Okay, what else? In the seed, we also have a namespace for the extension provider. Usually we have multiple replicas of them, and they are backed by a Kubernetes service. Okay, so then we also have introduced the Gardener Resource Manager as part of every shoot control plane a few weeks ago. It replaces the Kube add-on manager that we were using almost 2 years, I guess. And it's basically doing exactly the same like the Kube add-on manager, with the difference that it is a little bit more dynamic. So it reacts on CIDs, and not like the Kube add-on manager needs all the resources as static configuration. And this allows the extensions to dynamically add or remove resources. Okay, then let's now consider the Gardener needs to deploy some system component into the shoot. So what it does currently is it creates a secret, which then contains the Kubernetes manifest, the YAML or JSON of the resource that shall be created in the shoot. And after that, it creates the CID I just talked about, which is called managed resource. This is referencing the secret, and the Gardener Resource Manager is observing these CIDs and reacts on them, which is basically then creating whatever is part of the secret. So in this case, let's assume it's the deployment. This could be, for example, the VPN or whatever. Yeah. And now let's assume the Gardener extension for AWS needs to somehow modify this deployment, because otherwise it wouldn't work properly on AWS clusters. Could be anything. Could be some other command line flag or whatever. Yeah? Whatever is in the deployment spec. So what it does now, it also creates such a secret, which contains a webhook configuration. And then again, it creates a managed resource that references this new secret, which is again observed by the resource manager and then created in the shoot cluster. So now the shoot has a mutating webhook configuration that basically points to the extension provider. So the top left box. And whenever now this deployment needs to be mutated, the Kube API server of the shoot can cluster internally talk to the extension, because they both run in the seed. And because of the usage of the Gardener Resource Manager, it's also reconciled every time. So if the user changes the deployment or deletes the mutating webhook configuration, it is reconciled back to the desired state that is part of the secret. That's basically what we implemented. And with this in place, we could remove the 2 existing functions out of the Cloud Botanist interface that were mutating resources in the shoot. That was AWS that needed to change a config map of the Nginx ingress controller, because the load balancers work differently on AWS than on other providers. And I think Packet has injected some init container into the VPN shoot. So all of this provider-specific knowledge got removed out of the Gardener core code and moved to the specific extension provider repository. Okay, then I will show a quick demo how this looks like in the system. So here we have the seed cluster. As shown in the picture, we have a namespace called extension provider AWS with the extension controller, and this one is backed by the servers here. And then, of course, we have a shoot cluster where we can see the Kube API server and the Gardener Resource Manager and all the other components. And in this namespace, we have several managed resources that are all managed by the resource manager. They themselves reference secrets which contain the Kubernetes objects. And the one I just talked about is this one, the Gardener extension shoot webhook managed resource. This contains the mutating webhook configuration for the AWS provider. So when we now take a look into the shoot cluster and list the mutating webhook configurations, we see this one, which was created, and it is registered to create or update config maps. So when we now try to edit this Nginx config map I just talked about, we should see that the AWS webhook injects the needed configuration to make the Nginx ingress controller work on AWS clusters, which is specifically setting this property to true. So if I now try to set it to false or remove it, then I check it again, I see that it's set to true again by the AWS webhook. I can also entirely remove the field, and it's added back. And with this mechanism, the extensions can basically change anything that is deployed by Gardener. And it's also easy to implement for them because they can directly work on the resource like they do for the webhooks in the seed. They don't need to pass the managed resource and find out the correct secret that is referenced and then the correct object. This is all not needed now. It's way easier for them to implement it and way less code. Yeah, that's basically it. Do we have questions? In the Gardener extensions repository, we of course have implemented a library for all of this. So what the specific provider actually needs only to do is to register itself and to tell which resource it wants to change, and then just write the actual business logic that is then changing the resource. All of the wiring, which with the creation of the managed resource and secret object that is correctly referenced, and all of this is done by the library. Yeah. Thank you.
Thanks, Rafael. The next topic is Karydia. So Kristian, Lahmer, can you take over?
Hello, can you hear me?
Yes.
Great. So I try to start to share my screen.
You can see it.
Great. So hello from my side. I'm Kristian Lahmer. I'm currently working on a project called Karydia. Karydia is a Kubernetes add-on which helps to provide a secure by default setting. So Karydia is not Gardener specific. It's basically an Kubernetes add-on, which helps applications which runs on Gardener or on Kubernetes to have a better default settings for their pods. Because I think if you deploy a pod to the Kubernetes cluster, then the security settings are not that high. And I think the reason for this is probably, as with many other applications, that you start it once, then you set the first defaults, and then you have your first productive customers, and then you cannot change the defaults anymore, even so if it would be important, because you would break all the running applications. And maybe a second topic is also that Kubernetes would like to have an easy way to get applications up and running, and don't want to bother the developers too much in the beginning. But with these settings, you have severe issues in your clusters. For example, if you think about the security section of a pod, where you can specify a user, by default, a user is not specified. That means that your pod is running as root. Then the second topic which I would like to talk about is that a seccomp profile is not mounted by default, and so there are much more system calls available as it should be. And then one further topic is that the service account token is mounted by default. In most cases, this is not that a big issue, because the default service account token has not that much rights. But if you increase the rights of the service account token, and if you did not increase the rights of the service account token, and if you then create a new pod and the service account token is mounted, then this new pod has also the specific rights. And last but not least, I think you know that without any network policy, there will be any communication possible. So, and with Karydia, I would like to tackle this for security issues. Here you can see the default specification of a pod after you just created a pod. It's a very simple statement. This pod, for example, is just an Alpine image with a shell. And here you can see that, as I just told you, that the service account token is mounted. You can see that at the very bottom, and that there's no security section. That means this pod will run as root, and there's no annotation about a seccomp profile. So no seccomp profile is assigned here. So that means what we would like to do with, or what we do with Karydia is basically that we unmount the service account token by default. We restrict the system calls because we add a seccomp profile to any pod, and we also add non-root user. For example, we usually add user 1000 or max user. And we also have one more thing. So if you create a new namespace, then we add automatically a network policy which blocks the communication to different block the communication within the Kubernetes cluster. So we have here 3 levels. On the first level, we just block the communication with the host network directly. And we also block the metadata service of the host, of the infrastructure provider, and that's it. In the second level, which you can then choose as it fits to your cluster, we also block the communication with the internet. And in the third level, we allow only the communication within a namespace. So, and now I can show you a little demo how this looks like. So here I have here Now what I want to go to do, basically, I just want to start and just would like to, hello. I'd like to start a pod and go into the shell, and as you already have seen at the screenshot is that I'm now root in this cluster, in this pod, and basically I can connect to the internet. I can install curl, for example, and then I could, for example, get information from the metadata service. What else could I do? I think, I could just install kube control in this pod, and yeah, make it executable. And since I already have assigned some more rights to this service code token, I can just get the status of the cluster within this very simple pod. What I do next is basically I just install Karydia, and then you will see the difference. So we have a Helm chart here available. That was Tiller, sorry. So we have a Helm chart for installing Karydia. It takes a few seconds. Now it should be there, and the first difference which you can see is basically if we now create a namespace. Then after a few seconds, the reconciler hopefully will start and create a network policy in this namespace. In this case, we have just level 1. That means the communication to the metadata service should then not be possible anymore. Okay. Okay, the installation did not work of Karydia. This is bad. Let's try it again. Okay. Yeah, then I guess this demo will stop here. Sorry for this. I don't know what's going wrong, but I hope you got the point. So basically what we do is that we try to fix some common issues which happen in a development cluster. So then back to, no, that's the wrong presentation. Back to the presentation. So now you can see on this slide what I tried to show you in the demo. So on this slide, basically what I tried to show in the demo is that if I create a new namespace, a new network policy would be created, and then the communication would be restricted. And the second point, which would have come afterwards in the demo, is that if I create a pod, here you can see what then would be changed. The first point would be that we add a seccomp profile here. You can see that in this case we added the runtime default seccomp profile. You can configure your seccomp profile within our Karydia configuration. So that means, yeah, you can, for example, use the runtime default. If you would like to create your own seccomp profiles, then you can specify here your own. And we also take care that the seccomp profiles will be distributed to all your nodes in your cluster. And the second change, which you can see here, is that the security context will be set. That means we set here run as group and run as user, so it's not root anymore. And the third difference, which you cannot see because it's not there anymore, so there's no service called token mounted, so you don't see here the volume section of the pod description. So, and as a summary, I would like to say that the hardening of pods is really important. So the defaults are not enough. So if you use the defaults, then you run as root. If you and you have a service account token mounted, and there's no seccomp profile assigned, and communication within the cluster is pretty much open. And with Karydia, we try to invert all these defaults to a more secure pod in your cluster. So, and I'm already at the end of my presentations. Are there any questions?
Seems everyone is deeply impressed.
Hopefully.
Okay, thanks, Kristian. Then we can go to the last topic, serialized eviction of pods by Gaurav.
Hi, everyone. This is
Hi.
Gaurav. Let me share my screen. Is my screen visible?
Yes.
Okay. So the topic is machine drain. We have recently made some changes in how a machine is deleted. So when a machine is deleted, the pods inside that machine or that node are drained or evicted. So so what was the previous behavior? Previously, we used to evict all the pods parallelly. So the pods with PV or without PV were used to get evicted in parallel. So what the side effect was that in AWS and GCP, Amshu had done some tests and he found out that this was the behavior of when PVs were getting detached from AWS node or from GCP node. So from this graph, we can clearly see that as the number of volumes in the node increased, the total amount of time that the volumes took to detach in AWS case was also increasing. Similarly, for attach time with increasing number of nodes for GCP, the time it took to attach all those volumes increased. The side effect of all of this was that let's say there are 5 workload with PVs and all of them got detached in AWS, and so it took a lot of time, and for that time those 5 workloads will not be available to the customer or to the user. So they'll face a longer downtime. So the solution was implemented. The solution was to evict these pods in serial fashion instead of parallel. So that at one time only one of the workload is not available, and by the time the second workload will be evicted, the first one is expected to be scheduled on any other node which is available. So this was a small introduction about the solution of the problem that I just described. So I'll move to the demo. It's a very small demo. So what I have here is I have some pods, and these pods are created using deployments, and they have different priorities. So yeah, one thing I forgot to mention in the introduction part was that when evicting these pods with PVs, they will be evicted in the decreasing order of their priority. So the highest priority pod will be evicted first, so that it gets scheduled first, and then it is more available. So yeah, here I have 5 pods with different priority. So higher the number, higher is the priority. So priority 5 pod is the highest priority pod. And what we'll be doing is we'll be deleting the machine on which these pods are scheduled, and we'll see how these are getting evicted. So we expect them to be evicted one by one instead of all of them going into terminating state all at once. So first, let's get the node on which these pods are deployed. And here, what we'll do is we'll get the machine name on which for this particular node. So this is the machine that we want to delete, and we want these pods to get evicted one by one, for which I'll keep a watch for a terminating state, so that we can track what are the pods that are going into terminating state. And on this window, I'll be deleting this particular machine. And on the left hand side, what we expect to see is that priority 5 pod is being terminated first, and until its PV is detached, we don't move on to the next pod. And once the PV is detached for that pod, we move on to the priority 4 pod. So meanwhile, when so now that priority 4 pod is being deleted, we wait for PV to detach for that, and then we move on to priority 3. So in this fashion, the pods are getting detached from the node. Pods are getting evicted from the node. So this was a very small and quick demo, but yeah, that shows how the behavior of eviction in case of machine deletion is changed. So yeah, that's all. Does anyone have any question?
So you're saying that if the pods are evicted in series, then it's faster, or?
It is not faster, but the workload, the amount of time for which all the workloads are down is minimized.
Okay. Mm-hmm.
So the rollout can go slow, but the uptime of all the loads is going to be better.
So the impact is less, that it takes a long time to
right.
The PVs. Okay.
This was one of the features that helped in the rollout of the recent Docker image, the security fix. Basically, the downtime during that rollout would be reduced for our customers' workload as well as the shoot control planes.
I see.
So yeah, that was all. So thank you.
Thanks, Gaurav. Are there any other questions to Gaurav? If not, then we are at the end of today's meeting. Thanks everybody who presented, and see you next time. Bye.